So chapter 2 deals with atoms, molecules, and ions. We're going to start looking inside the atom and how it's arranged and what's going on in there and why are things attracted to other things. And we're going to end this chapter with ionic bonding. So this is our Bible from this point on, the periodic table. If you have the book, there's the exact periodic table that is placed in the cover of this book. Okay, so you'll always have a periodic table on you if you have the book, or you can always look one up or come back to the slides, whatever it is. We're going to talk about the breakdown, but I want you to just point out this one is color-coded. The majority of the elements out there are metals. We do have some non-metals, and we have these things called semi-metals or metalloids right in the middle. Okay. And we'll talk all about the breakdown and all that fun stuff in this chapter. So let's talk about matter. Remember, matter is anything that has mass and takes up space, so mass and volume. All right, and that's what chemists are studying. So we'll start with the simplest type of matter, all right, that has unique chemical and physical properties, and that's an element. An element is made up of one type of atom. It could be a single individual atom, or it could be molecules of an element. So what I mean by that is oxygen and nitrogen and hydrogen and fluorine and chlorine and bromine, they all exist, and iodine exist in nature as two elements. All right, or sorry, two atoms of the same element bonded together to form a molecule. O by itself isn't stable, so it bonds to another O to make O2. The majority of our elements are just individual atoms of said element moving around, but some need to partner up, all right, to give stability. But elements are the smallest type of matter that have unique chemical and physical properties. Okay. You can't break it down any simpler, all right, without losing those properties. Yes, inside we know that there's protons, electrons, and neutrons, but a proton's a proton, electron's an electron, a neutron's a neutron. If I were able to crack elements open, like crack open a sodium and dump the contents into a beaker, and do the same thing with, let's say, a sulfur, or, doesn't matter, a potassium, and dump the contents in, I can't pick out what protons came from what. It's the arrangement and the number of protons and the electrons and the neutrons that give an element its properties. So, yes, there's smaller matter inside the element, but the element as a whole, the atom of the element as a whole, is the smallest type of matter that has unique chemical and physical properties. Molecules, when they form, they behave as independent units and move around. So, sodium, okay, has specific melting points, boiling point, color, density, how it reacts in water, how it reacts with acid. It has specific chemical and physical properties. Chlorine has specific chemical and physical properties. We could bring those together and do a chemical reaction where we take on new chemical and physical properties. Sodium reacts violent with water. So if I were to put a piece of sodium in my mouth, it would be an exothermic reaction, meaning it gives off heat. It's so exothermic that one of the byproducts is hydrogen gas. It can ignite the hydrogen gas. So essentially, you eat a large enough piece of sodium, you die. Chlorine gas is that yellow gas you see in the slide here. It's thick, it's noxious, and it'll kill you if you inhale it. However, if I take an element of sodium and an atom of chlorine or Cl2 gas and I interact them together, I get this white powder out. This white powder has a new melting point, a new boiling point, has a different color, has a different density, doesn't react violently with water. We can eat it and not die in small enough quantities. It adds flavor to our food. If I start, and we talked about this in chapter 1, with two or more different things, and I start where one or two or three different things and start and end up with something new, I do a chemical reaction. And in that chemical reaction, here's the big key. The atoms are conserved. Sodium's still sodium and chlorine is still chlorine. However, when they combine with one another to form a molecule, Okay, or form an ionic bond. They take on new chemical and physical properties. So, what are we talking about? A compound is formed. A compound is a substance where two or more elements are chemically combined. Okay? Now, if I were you, okay, somewhere if you are taking notes, I would make two columns here. Something like this. All right? And say, essentially, here's a compound, and here's something known as a mixture. And there's differences between the two. Okay? A compound is chemically combined, while a mixture is physically combined. All right. A compound has a specific ratio, meaning no matter what its source is, it'll always be that ratio. The example everyone always uses here is sodium chloride and H2O are compounds. Salt water, sodium chloride and water is a mixture. Okay, you could have different ratios. And what I mean by that is this. The water you drink is the same chemical makeup as the water that's in a lake, that it's water that's in an ocean, water in a toilet. It's all water. It's all H2O no matter what its source is. However, salt water, okay, I could have a ratio that I gargle with, but that's going to be different than the ratio of salt to water in the Atlantic Ocean, which is going to be different than that of the Dead Sea. Since I'm chemically combined, a compound, all right, needs a chemical reaction to separate it. Mixture, I could do a physical change to separate it. So to separate water into hydrogen and oxygen, its components, I need to run electrical current through it. To separate salt water, if we're going to stick with that, okay, all I have to do is evaporate the water off. I still have water vapor, it didn't do a chemical change, and then I'll have the salt. Okay. Last but not least, compounds, when they are formed, take on new properties. They do not retain the properties of what makes it up, as we saw with sodium and chlorine. Sodium had specific stuff, and if we eat it, we die. Chlorine gas could kill us. Put them together, and we have salt, table salt. Mixtures retain the properties. Salt water is salty and it's water. So mixtures retain the properties that make them up. So compounds are chemically combined. Mixtures are physically combined. Compounds have specific ratios. Mixtures have different ratios. Compounds require chemical reactions to separate them. Physical changes to separate mixtures. Compounds take on new chemical and physical properties, while mixtures will retain some of the properties of what makes it up. So it all depends. So salt water is a mixture. It contains two compounds, salt and water. Okay. Now, there's two types of mixtures out there. Homogeneous mixtures and heterogeneous. Hetero meaning opposite, homo meaning same. Heterogeneous mixtures have one or more visible boundaries between the components. Okay. Homogeneous mixtures, there's no boundaries seen. They're all in the same state of matter. Air. Okay. Salt water, where all the salt is dissolved. Heterogeneous mixture would be, beer, champagnes, things like that. Carbonated drinks, soda. because you could see the gas in there and you could see the liquid. Now, solutions are very important. They're homogeneous mixtures. And if they are dissolved in water, they have a special name, and I have it here in like a brownish red color, an aqueous solution. Okay. Aqueous solutions means that the substance is dissolved in water. Aqueous solutions are so important that Chapter 4 is dedicated just to aqueous solutions. Okay? So, when you finally have lab, right, you'll be using different techniques to separate mixtures. Okay? And here's all the different techniques. Filtration separates via particle size. We use a piece of filter paper just like old time making coffee. Use a piece of filter paper so that the coffee doesn't go through and the caffeine and water run through to make your pot of coffee. Crystallization looks at solubilities based on temperature or pH, where one will be soluble and one won't be. Distillation is probably the one you guys are most familiar with, because that's how your alcohol is made. Extraction, again, differences in solubility, and chromatography. Now, I'm not going to sit here and go through all of these because we would talk about these in lab, but you can look through. This is, if you have to take orgo at some point in time, all right, this is what we're going to be making, distillation apparatus, but this is essentially how they make your alcohol. This is what the moonshiners are doing. You put your alcohol in here, it heats up, it vaporizes, comes across, cools in this condensing tube, and is collected over here. And the way you know if you're collecting the alcohol or not, there's a thermometer here, and each substance has its own vapor temperature, and that's how you'd know what was coming over. Extraction is another thing you'll do in organic chemistry, and there's lots of different chromatographies that are based on either solubility or particle size and so on. Okay. So in sample problem 2.1 from the book, it says, which of the following designates or is distinguishing an element, a mixture, or a compound? Okay, A is a mixture. I've got all these different types of I've got all these different types of compounds in there that aren't chemically linked to one another. They're just moving around. This is definitely an element because it's made up of only one type of atom. And this is a compound because there is a specific set ratio. It looks like one black and a bunch of blue around there or something like that in this picture. But again, all of the individual molecules are the same. It's not a mixture, and they're all chemically combined here, so that's a compound. All right, questions on compounds, mixtures, anything like that? So if we look on a periodic table and we look at our elements, the majority are individual atoms. One atom, helium, neon, boron, so on. Some are diatomics, and you should be familiar with your diatomics. Hydrogen, H2, oxygen, O2, nitrogen, N2, bromine, chlorine, fluorine, and iodine. They appear in nature as two atoms of the same element combined with one another in order to give extra stability. Some of our elements could also be polyatomic, meaning many, not diatomic, meaning two, but many. Ozone is an example. Ozone is 3 oxygens bond with one another. Another one out there is P4. Phosphorus appears in nature as 4 phosphorus. selenium, and sulfur, okay, appear as octatomic molecules, meaning they're 8 linked together in nature to give stability. Now, I'm going to tell you this. You should know your elemental symbols. You should become familiar with them. Okay? You should be well aware of what the element's name is and what its symbol is. It's going to help you in the naming process as we move forward. Okay. So we already talked about the law of conservation of mass. Okay. And I'll explain what these postulates mean and all of that. But the law of conservation of mass says mass can't be created nor destroyed, which means that if we start with something in a chemical reaction, it has to be found on the product side. So in a chemical reaction, this is known as the reactants over here. These are known as the products. Whatever appears over here has to be accounted for over here. It doesn't have to be the same compound. It could create a new compound, but it has to be accounted for. The law of constant composition, basically, there's the full definition. What it's saying is that a compound's ratio does not change. If you change the compound's ratio, you change the compound. Essentially, water's water, no matter what. So if you drink bottled water, you're paying for water. Your body doesn't know that, it was, filtered through, the lava ash of a mountain that hasn't been touched by humans in 1,000 years, so we're going to charge you $15,000 for a bottle. Your body sees 2 hydrogen and oxygen, it says it's water, let's utilize it as water. It's the same thing when people say, sea salt is healthier than regular salt. It's sodium chloride. Your body sees it as sodium and as chlorine. It doesn't know that it came from nature. It doesn't know that it was made in a lab. It sees sodium and chlorine and breaks down the ions and does what it's supposed to do. Okay? But it's natural. Well, so is snake venom. And I don't see any of us running out to get bit by, a cobra anytime soon because it's natural. All right? Just because it's natural doesn't mean it's beneficial. It's sodium chloride in a chemical standpoint. Okay, so your body doesn't know the difference whether it came out of the Morton bottle that Morton made in the lab or it was sea salt out of, whatever sea. Now, there are different types of salt out there. There's pink salt and blue salts and all of that. Those are different because those have different chemical makeups. Therefore, they'll have different tastes, they have different ions, and so on. Law of multiple proportions basically states that when elements combine, they have to be in whole number ratios. They can't be halves and quarters and things like that. So that's what those laws are stating. And we'll talk about the postulates in a little bit. Okay. And this is just summing up those things, those laws, and giving you a quick rundown of them. Now, let's look at the sample problem that basically dictates the law of constant composition here. Okay, the sample problem states analysis of 84.2 grams of a compound containing uranium showed that 71.4 grams of it was uranium, with the other grams being oxygen. How many grams of uranium are in 102 kilograms? So what they're basically telling you here is if I analyze a small sample and find the ratio, I can apply it to any size sample. Okay, so they're saying that they took 84.2 gram sample, and the 84.2 gram sample has 71.4 grams of uranium. Okay? Which means that if I do the math and I figure out the percentage, 71.4 over 84.2, part over the whole, if you don't remember how to do percentages, all right, or figure out the ratio, that's what we're doing here. A ratio is just the fraction without multiplying it by 100. 71.4 divided by 84.2 equals 0.848. So that means that no matter what sample size I take, it'll always be a ratio of 0.848. So they say how many grams of uranium are in 102 grams of this compound. So now I have a 102 kilogram sample. The first thing I want to do is turn it into grams, which would be 102,000 grams. And how much would be uranium? Well, 84% of it, or multiply by the ratio we got. And we take 102,000, multiply it by 0.848, and I'm getting 86,500 with sig figs grams. Okay? So all they're asking in a problem like this is saying, if you know my percentage in a sample size, I can apply it to no matter how big the sample size is. So for instance, with water, okay, another example we'll do. This is not in the slides. This is just me doing this. Water has a mass of 18 grams, and we'll get to that later on. The water has a mass of 18 grams. Okay? Hydrogen, so water's H2O. Hydrogen is 1 gram, and we have 2 of them, so 2 grams total. Oxygen is 16 grams, and we got 1 of those, so 16 grams due to oxygen, and that's where my 18 grams comes from. Well, if I want to know my ratio of hydrogen, it'd be 2 over 18 would be hydrogen, or 1/9. Okay, which is roughly 11%, give or take. It's like 11.1%. And oxygen would be 16 over 18, which would be 8/9, which is approximately 89%. And as a ratio, this would be 0.11, and this would be 0.89. So if I had, 2,000 grams of water, and I wanted to know how much hydrogen is in there, I would take 0.11 times that. If I want to know how much oxygen, 0.89. It doesn't matter the sample size, because the law of constant composition basically says if this is what my ratio is, it's always my ratio no matter what amount of sample I have. Okay? Questions on that? Okay. Questions? All right, law of multiple proportions we talked about. We'll look there. So let me know if you have any questions. I can get a little drink here. Okay, if no questions, then I'm going to move on. And let's talk about the atom. So we're going to talk about the atom, little general ideas of how they found what they found. The first one to come out with something was the atomic theory of matter, was John Dalton. He wasn't the first. I mean, people were thinking about this since, the ancient Greeks. But John Dalton started putting things together and coming up with what was known as the atomic theory, and that's what those postulates meant. He said, what makes substances different from one another is the fact that there's these little tiny things that we can't see, okay, that are making up the matter that we are witnessing. And that's why, for instance, a rock is different than water and so on. He says that all atoms of an element are identical. They have the same mass and the same chemical properties, and they are not changed in a chemical reaction. Now, they can combine to different things, but they are not changed in a chemical reaction. Okay. So, here's his, theory all down into his postulates. All matter consists of atoms. Atoms of one another cannot be converted into atoms of another, which was a big deal because at the time that he's stating this, alchemists were one of the things they were trying to do was convert one metal to another. They did a lot more and contributed a lot more to science than people give them credit for. But they always get hung up that they were trying to turn, lead into gold, which isn't possible. Atoms of an element are identical in mass and other properties, and compounds result in specific ratios forming. Okay. Well, all of these postulates can explain all of the laws that we now accept. Atoms can't be created or destroyed. Okay, converted in other types of atoms and so on. And during a chemical reaction, so it explains the mass laws. It explains the laws of definite composition. And it explains the multiple proportions. So Dalton starts laying down the groundwork for us to start working inside and figuring out what's going on inside the atom. Now, in a normal lecture setting with a normal exam, I would normally talk about this history and the discovery of the atom and all of this stuff. And I would expect you to write an essay on one of the experiments. I'm not going to do that here. Okay, if you want to read about the experiments and everything, they're awesome. I think it's really interesting. But for time's sake and the fact that you're not going to be writing essays on the exam and things like that, I'm going to skip over it. It's in the book, it's in the slides, and you could talk about it. But I will essentially say, I'll give you the rundown of everything that they found here. Okay? The one thing I want to point out is right here. Okay? The research starts the late 1800s. And they find electrons, protons, neutrons. So late 1800s, early 1900s, they go through knowing nothing about the atom. To 1932, they find out, finally, the last piece, the neutrons. They find out that the protons and neutrons are in the nucleus, which we'll talk about. The protons are positively charged, the neutrons have no charge, and the electrons are negatively charged. And, roughly 15 years later, 14, 13 years later, a decade later, we're dropping the atomic bomb, and I'm not getting into the morality of the atomic bomb, I'm just saying the science and the development of doing so. So no computers, no nothing, none of that. And when they redid all of these guys' experiments with modern technology, they were right on. The only difference is scientists could carry it out to further decimal places. So they went from knowing nothing of the atom to being able to split the atom and harness its energy in a matter of 50 years, roughly, without computers or anything like that, which is just astonishing in my mind. I know you don't get as excited as I do about it, but I think it's amazing what these people were able to do. So, what did they figure out? Okay, here's what they figured out. They figured out in their experiments, Chadwick and Rutherford and Thompson and Millikan and all these guys figured out the following. Our atom has a nucleus. Inside the nucleus are neutral charged neutrons. Okay. Positive charged protons. And on the outside are negatively charged electrons. At one point in time, they thought that the atom was this giant negative charge called the plum pudding model with little positives moving around in it. Okay. So what to point out on this? Well, the mass of a proton is roughly 1.68 times 10 to the negative 24th. And I'm not going to expect you to know the mass of a proton or a neutron or electron, but they're up here for this reason. Protons contain a positive charge 10 to the negative 24th. Neutrons don't have a charge, but their mass is times 10 to the negative 24th, roughly the same mass. Electrons' masses are 10 to the minus 4th smaller. So 0.0001 smaller than a proton and a neutron. So what does that mean? What that means is that if I'm looking at the mass of an atom, it really comes down to the mass of the nucleus or the mass of the protons plus the neutrons. Electrons are so small. Now they're important because electrons are going to balance charge. But for mass-wise, they play no role in our mass. So scientists created something called the atomic mass unit. So instead of having to write 10 to the minus 24th every time, they basically say AMUs, which they mean they're totaling up the number of protons and neutrons because this is roughly the mass of a proton or a neutron. In an atom that doesn't have a charge, so here's some stuff to write down. The mass is protons and neutrons. In an atom with no charge, the protons equal the electrons. Okay. So, how could I tell how many protons an atom has? And here we go, and I'm going to show you, going back to the periodic table, right here. On my periodic table, there's a couple things. Basically, why I said it's our Bible is because we could find everything that we need to know. This here, these numbers on top, are known as the atomic number. All right, atomic number. It tells us the number of protons. All right, it's an atomic number. It tells us the number of protons. It is the fingerprint of the atom. If you change the atomic number, you change the atom. You cannot change the number of protons. The protons is the fingerprint. You change the number of protons, you change the atom. I can lose electrons, I can gain electrons. I could lose neutrons, I can gain neutrons, but I can't change the number of protons without changing the atom. That's known as the atomic number. Also on our periodic table, we have the atomic mass, which we'll talk more about that later. And we have our atomic symbol. And those symbols, they're weird sometimes. Some of them come from Latin, like sodium is Na. Why is it sodium and Na? Well, that's natrium. Okay. And then you come over here, some of them are simple. Carbon is a C, nitrogen's an N. But then you get down here to something like Sb, and that's antimony. Okay. So, again, there's a rhyme and reason to what's on the periodic table. If you named it, then you got to essentially either name it in Latin, Greek, or name it after someone. Okay. So let's talk about these protons, electrons, and neutrons real quick, and looking at an atom and all of that. So, by looking at the periodic table, we're able to tell, okay, how many protons, electrons, and neutrons something has. And we write it in this form. All right, and we'll start with, well, you know what? Let me use an X here to do this instead of a C. Okay. Yeah, let me use an X because that's, I just want to see what letter they used on the slides just so I stay consistent. This is known as the XAZ form. Okay, where A tells you the mass number and Z tells you, so this tells you the mass number, which is the number of protons plus neutrons. Okay, this tells you the atomic number. Sometimes they don't give that to you because they expect you can look it up on the periodic table. So if you see something like this, C12, 6. Okay, 12 is the mass number. 6 is the atomic number. Sometimes, like I said, because you can look the atomic number up on the periodic table, they might write this similar, like just like that, saying that you can go look up that number, or you might see it written in longhand, carbon 12, like so. But just given this information, you should be able to tell me how many protons, how many electrons, and how many neutrons you have. Well, proton-wise, the atomic number tells me the number of protons, 6. In a neutral atom, there's no charge on my carbon. Electrons equal the protons because the positives and negatives have to cancel out. And mass number is 12, is protons plus neutrons. Well, if it's 12 and I have 6 protons, I must have 6 neutrons. So 6, 6, 6. And for those of you who have to take organic, you'll realize that carbon is the devil. All right. And it works out perfect. Okay. Now, there are different terms to talk about. Isotope, which essentially has same protons, different number of neutrons, therefore a different mass. So an isotope is something that has the same number of protons, a different number of neutrons, therefore they have a different mass. And then there's something known as an ion that has a difference in electrons to protons, which gives a charge to the molecule. And we'll get more into ions and things like that and more into isotopes. But I want to just include all those right now for this reason. What if I was given the following? Okay, Na23, Na23 plus, and Na22. And I want to know the protons, the electrons, and the neutrons for all three of these species. Okay, well, I'd look at the periodic table. I'd find Na, I'd find the atomic number, and the atomic number of sodium is 11. So sodium's atomic number, so this would be sodium's atomic number is 11, which means that every one of these is sodium, so every one has to have 11 protons. There's no charge on this sodium, so the electrons have to be 11. And 23 minus 11 gives me my neutrons, so there's 12. All right, so let's look at this one. Sodium, 11 electrons. Well, now I have a plus charge. Well, that means I have to have one extra proton to have that plus charge. So it'd be 10. 11 protons, 10 electrons. The electrons cancel out 10 of the protons, leaving one left to give me the positive charge. And then to figure out the neutrons, it's 23 minus 11 and 12. Come over here. No charge. So they have to equal one another. Now it's 22 for the mass, 22 minus 11, and 11 there. All right, questions on how to find protons, electrons, and neutrons in an atom? Or where I got the numbers from, or anything like that. Let me know now. Because I am done and I'm looking for the homework right now. Wow. Like a good sneeze, right? Are we sure we don't have anything? I know I threw a bunch at you today. Thank you, Ellen. Came out of nowhere. All right, here's the homework then. Try sample problem 2.4 on the slides. Page 86, 2.1 to 2.5. Page 87, 2.9, and 2.20 to 2.25. And page 88, 2.36 to 37, and 39 to 46. That should cover everything we did today.